I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering. I am going to give a series of video lectures on the subject microprocessors and the microcontrollers. This is the subject for 6th semester for ECE branch. Today the topic what I am going to deal is register organization of 8086 microprocessor. So this topic is part of the module 1, and in module 1 we are going to cover the topics register organization of 8086, architecture and signal descriptions, memory organizations, general bus operations, minimum mode, maximum mode, and machine language instruction formats and addressing modes, and assembly directives and operators. So these are all the topics which will be covered in module 1. And today I am going to discuss about the register organization of 8086. So what is a processor? A processor is a logic circuit that responds to and processes the basic instructions which drive the computer. So the term processor is generally replaced the term central processing unit. The processor in a personal computer or embedded in small devices is often called a microprocessor. So microprocessor, it consists of general purpose registers, timing and control unit, etc. And it gets instructions from external memory. And what is a microcontroller? Microcontroller, it has internal memory wherein the program can be stored. And in addition to memory, it can have few I/O devices like A to D, D to A, like that. So microprocessor is bigger than microprocessor is a subset of microcontroller. So the processor or CPU is a computer's brain. So this allows the processing of numeric data, meaning the information entered in binary form. See, the language of microprocessor is zeros and ones. So whatever program we write, that we write in terms of assembly language program, and this assembly language program is converted into machine language by the compiler, which is understood by the CPU or the microprocessor. So the evolution of microprocessor is like this. Intel has made 4004 microcomputer in 1971. So this was a 4-bit microprocessor, and this was based on PMOS technology. See, the MOSFETs are basically classified into P MOSFETs and N MOSFETs. In P MOSFETs, the majority charge carriers are holes, and in N MOSFET, the majority charge carriers are electrons. And this contained approximately 2300 P MOSFETs. And subsequently, Intel has made 8008 microprocessor in 1972, and this was 8-bit microprocessor. 4004 was 4-bit, and 8008 is 8-bit. And this also was based on P MOSFET technology. This also was based on P MOSFET technology. Next, subsequently, Intel has made 8080 CPU, and that was 8-bit, and this was made in 1974, and this was based on NMOS technology. This was based on NMOS technology. See, NMOS technology has its own advantage that operating speeds are high, because the majority charge carriers in N MOSFETs are electrons, and as you know, the mobility of electrons is more, you get high operating speeds. Then Motorola has come up with its own microprocessor MC680, and this was 8-bit microprocessor, and it was based on a single power supply. This required a single power supply. That was the advantage it had. So naturally, everybody started purchasing the microprocessors from the Motorola. So then Intel has come up with 8085 microprocessor, that was 8-bit microprocessor, that also was based on single power supply. Then the evolution has started towards the 16-bit microprocessors, and 8086 is a 16-bit microprocessor, and this was also requiring a single power supply. Then subsequently Intel has made 32-bit, 64-bit processors. So this is how the evolution has taken place. And the microprocessor is a backbone of computer system, which is called a CPU. And microprocessor speed, it depends upon the processing speed, and it depends upon the data bus width. See, higher the data bus width, you get higher operating speeds. So a common way of categorizing the microprocessors is by the number of bits which the ALU can work at a time. ALU works on the operands. If ALU can operate on the 8-bit operands, then we call the processor as 8-bit microprocessor. And if the ALU can operate on 64-bit operands, then we call the processor as 64-bit processor. So the address bus, there are basically 3 buses in a CPU: address bus, data bus, and control bus. So the address bus is unidirectional because the address information is always given by the microprocessor to the memory or IO devices. So it is a one-way communication. And the data bus is bidirectional. Suppose the microprocessor is writing data to the memory, then the flow of data is from the processor to the memory. If the microprocessor is reading, then the flow of direction is opposite. So the data bus is bidirectional because the same bus is used for transfer of data between the microprocessor and IO devices, including memory. So most microprocessors have limitations on the size of data, and most of them do not support the floating point operations. So the storage capacity is limited in a processor, and it has a volatile memory, and you can use the secondary storage devices, and the secondary storage device capacities are larger, and it is a non-volatile memory type. So you can have primary memories or you can have the secondary memories. What are the primary memories? RAM, that means read write memory, and it has high speed and it is volatile type. And ROM also is primary memory device. The secondary devices are floppy disk and hard disk are the secondary devices. And what is a compiler? This is used to translate high-level language program into machine language code at a time. So this does not require special attention to store in a memory. It stores automatically. So the execution time is less compared to the interpreter. Now let us come to the architecture of 8086 microprocessor. This is a 16-bit microprocessor. That means the ALU can operate on 16-bit data, and all the internal registers, they can work with 16-bit data. And 8086, it has 20-bit address lines, so it can access up to 1 megabyte of memory, that is 2 power 20. See, if a processor has 4 address lines, it can access 16 memory locations with 4 address lines. Now 8086 has 20 address lines, which means that you can operate with 2 power 20 bytes of memory. 2 power 20 means what? 2 power 20 is equal to 2 power 10 into 2 power 10 bytes. So 2 power 10 is 1k multiplied by 1k. So this is equal to 1 megabyte. Okay. And 8086, it has 16-bit data bus. So this can read or write data either 8 bits or 16 bits. So though it can work with 1 megabyte of memory, as far as IO devices are concerned, only 16 address lines are used. So with the 16 address lines, you can have how many IO devices? 2 power 10 into 2 power 6. So 2 power 6 is 64. So 64k IO ports, they can be connected to the 8086 microprocessor. So it has many general purpose registers. It has 14 general purpose registers. So these registers are 16-bit registers, and the frequency range of 8086 is 6 to 10 megahertz. So this clock has to be given by the external clock generator to the 8086 microprocessor. 8086 microprocessor, as you see in this diagram, it is available in 40-pin dual line package. So these are the 40 pins. You can have, starting from 1 is ground and 40 is VCC, and there are pins which are specific to the minimum mode. There are pins which are specific to the maximum mode, and there are signals which are common to both minimum and maximum modes. So these minimum and maximum modes we'll discuss in next series of lectures. So as you see from the pin diagram, the microprocessor has 20 address lines, and out of these 20 address lines, AD0 to AD15, they are used both for data and address. So these are 16. And how many more lines are left out? 4 lines are left out. They are A16 to A19. These are 4. So total you have 20 address lines. So these AD0 to AD15, they are used both for address and data. It is a time multiplexing. When address is available on AD0 to AD15, ALE signal is made high, and other times when ALE signal is low, that means the information what is present on AD0 to AD15 is data. So this 8086, it works with a single phase clock with 33% duty cycle to provide internal timing. That means for 33% of the time it is on, the remaining time it is off signal. That means 67% time it is off. That means the signal is like this. 50%. What is 50% duty cycle? This is called 50% duty cycle with equal on and off periods. But here this is a asymmetric clock with 33% duty cycle. That means it is like this. The on time is less, the off time is more. So this works with 33% duty cycle to provide internal timing. And this can prefetch up to 6 instruction bytes from memory, and it queues them in order to speed up the instruction execution. So the instructions can be fetched in advance from the memory, and they are stored to facilitate pipelining. And it requires a single plus 5 volts power supply. And of course, just now we discussed that it is a 40-pin dual line package, and this can be designed to operate in 2 modes, minimum mode and maximum mode. So the minimum mode is selected by making the Mn by Mx bar signal high. There is a pin, Mn by Mx bar pin. So if this Mn by Mx bar pin, if it is connected to VCC, if this pin is connected to VCC, then that means that it is in minimum mode. If this pin is connected to ground, if low, let me say, then it is in maximum mode. So what is a minimum mode? Minimum mode is a single processor communication and maximum mode is a multi-processor communication. So let me draw the functional block diagram of this 8086 microprocessor. So the 8086 microprocessor architecture, it consists of basically two sections, the bus interface section and the execution unit section. And this is the memory. External memory is here. So this I will call it as memory interface. Okay. And this is connected to ALU in the bus interface section. This is the ALU which is present in the bus interface section. This ALU is responsible to generate the physical address. There are registers where the base address is stored and those registers are CS, DS, ES and SS. So this is CS register, which is a code segment register, and followed by DS. DS is data segment register, followed by ES is extra segment register, and this is followed by SS is stack segment register, and we have the IP, instruction pointer. So the instructions from memory are fetched in advance and they are stored in FIFO, that is first in first out register, which is of 6 bytes length. This is of 6 bytes length. Okay. And from the instructions, they are passed on to control register for decoding. These are control register which does the instruction decoding. Okay. So this is all the bus interface unit. In the bottom, I have the execution unit. The execution unit, it contains point registers and the general purpose registers which are used for arithmetic and logic operations. So these are the various registers. This is AX, BX, CX and DX, followed by stack pointer, then base pointer, then followed by the source index and DI, the destination index. And here there is an arithmetic and logic unit which performs the logic and arithmetic calculations. This is the ALU. And here we have operands and flags. So this section is called as BIU, Bus Interface Unit section, and this is EU, Execution Unit section. So this is about the architecture of 8086. So we have total 14 registers in 8086. Those 14 registers are AX, BX, CX, DX, and we have the segment register, 4 segment registers. They are CS, DS, ES, and SS. And we have the point registers IP, then SP, BP, and SI, and DI. So how many registers? These are 13. So the 14th register is flag. So there are 14 registers. So all these registers are 16 bits. So the register AX, it is basically used for multiply and divide and IO instructions. This is also called as the accumulator register. And AX, we call it as AL and AH. AL is the lower byte of AX register and AH is the higher byte of AX register. So these can be combined together and they can be used as a 16-bit register AX. Okay, so AL contains the low order byte of the word and AH contains the high order byte. So the accumulator is used for IO operations and string manipulations and also for arithmetic and logic computations. The base register, which is also called as BX. So the BX also divided into BL and BH. So BL is 1 byte, which is a lower byte, and BH is higher byte. So they can be combined together and they can be used as a 16-bit register BX. So BL contains the low order byte and BH contains the high order byte. So BX, it usually contains a data pointer for based or based indexed or register indirect addressing. So this also can be used in loop or shift rotate instructions, and also this also can be used as a counter. On the other hand, CX register is also called as count register. This contains CL and CH. CH and CL. So this is 8 bits. This is 8 bits. That means this is 1 byte. This is 1 byte. And both of them together form a 16-bit register. And this is basically used for the count purposes in string manipulations. Data register is nothing but DX register. And this contains DL and DH, and they can be combined together and used as a 16-bit register DX. Okay, so when combined, DL register contains the low order byte and DH contains the high byte data. So this register can be used as a port number in IO operations. So for port operations, this contains the port address and this can be used in indirect addressing mode for IO operations. In integer 32-bit multiply and divide instruction, the DX register, it contains the high byte of the result. Okay. So here, maximum how much memory we can have in 8086, we have discussed that there are 20 address lines, so we can interface 1 megabyte of memory using 8086. So the base address is stored in the segment registers. Uh, the segment registers are code segment, data segment, stack segment, and extra segment. And the offset address is stored in the point or index registers. Okay. So CS register, it contains the base address of the executable code of the main program. And the corresponding offset register for CS is IP. So IP contains the offset address. So offset address, it indicates the distance of the memory location from the base address. The base address is stored in the segment register. The offset address is stored in the pointer registers. For example, let us consider the case of code segment. So code segment, the starting address is stored in CS register and the offset address is stored in IP register. So what is the offset address register size? This is 16 bits. So when there are 16 bits, you can have the offset address in the range 000 to FFFH. So each digit is 4 bits. So we can have the address range from 000H to FFFH. So total how many memory locations? 64 kilobytes. Okay. So you can have a maximum code size of 64 kilobytes. Similarly, DS contains the base address for the data segment and the corresponding offset address is stored in SIR BX. And stack segment, the important data is stored with the CPU in the stack and this is retrieved in times of need, and the stack segment also has a pointer register SP and BP, which is a 16-bit. And the extra segment, this is used to store the additional data. Okay, so all these segments, because they have offset registers of 16 bits, so each segment can be of 64 kilobytes. So there are 4 segment registers. So 64 kilobytes into 4, so you can have total 256 kilobytes. Okay. So the 1 megabyte of memory can be, we have total 1 megabyte of memory. Okay. So for 1 megabyte of memory, how many logical segments you can have? You can have the segments of 256 into 16. So you can have so many logical segments. See, the maximum size of the segment is 64 kilobytes, but if your program is less, you can have lesser size also. So total maximum you can have, you can have 16 logical segments if each logical segment is 64 kilobytes. But suppose your program is less. In that case, you can have more than 16 logical segments. So as you see here, the base address is stored in the segment registers. Now let us say the base address is let us say the base address is 8A0F. Okay. Let the offset address be 1A00. Okay. So what is the base address? 8A0F. So 8 means 1000. A means 1010. 0 means 000. And F means 1111. Okay. Now To the base address, 4 zeros are added and they are shifted leftwise. The base address is shifted leftwise by 4 bits. So when it is shifted left side by 4 bits, then 4 zeros are added to this. Now to this, that means the 16-bit data has become 20-bit data. And to this, the offset address is added. What is offset address? 1, 0, 0, 0, 1. Then A. A is 1, 0, 1, 0. Then 0, 0, 0, 0, 0, 0, 0, 0. Okay. So then the offset address is added to the base address. So what is the total address? 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, then 1, 0, 0, 0. So this is the actual physical address. So you get 0, F, A plus 1 is B. So this is the 20-bit physical address, 8B, AF, 0. So this is how the physical address is calculated. So the offset address, it indicates the distance of the memory location from the base address. So what is the maximum you can have? Maximum is when you get all F's. Minimum is all zeros. So you can have a range of 0 to all F's. That means 64 kilobytes. Maximum offset you can have. So this is how the physical address is generated using 16-bit registers. So the 16-bit base address is stored in CS or DS or ES or SS, and the offset address is stored in IP or SP or BP or SA or DA. So these are taken, and in the ALU of the bus interface unit, the 20-bit physical address is generated. So what is the purpose of bus interface unit? This essentially generates the physical address for communicating with I/O devices including memory. The bus interface unit also has instruction stream byte queue, which is 6 bytes. So here the instructions are prefetched well in advance, 6 bytes dimensions. See, in a normal processor like 8085, the sequence of operation is like this. First the instruction is fetched, then it is decoded, then it is executed. So when the first instruction is getting, unless the first instruction is executed, there is no operation on the second instruction. Only after the first instruction is fetched, decoded and executed, then only the second instruction is fetched in earlier processors. So the CPU, which has 3 blocks for fetching, decoding and executing, they are not effectively utilized. Unless the first instruction is executed, then only the second instruction was fetched. That means when the first instruction is getting fetched, decoded and executed, some 2 blocks are idling. So to have the effective utilization of the microprocessor, pipelining is included. So in pipelining, what happens? So this is fetch, decode, execute. Okay. So the first instruction is fetched. This is the first instruction in the first cycle. So these two are okay. Next, what happens? The first instruction goes to the decoding. Then at the time, the second instruction is fetched. In the next stage, what happens? The first instruction gets executed. The second instruction enters into the decoding stage, and the third instruction gets fetched. So this is how the fetch, decode, and execute all the blocks are effectively utilized. So this is called pipelining, and this pipelining is facilitated by this instruction stream and byte to queue register. And 8086, it has flag register. The flag register, depending upon the result of the from the accumulator, the corresponding flags are set. The flag register is a 16-bit register, and this is the format for the flag register. This has carry flag, followed by the parity flag, followed by the auxiliary carry flag, followed by the zero flag, then sign flag, T flag, I flag, D flag, and overflow flag. Okay. So out of these 9 flags, 6 flags are conditional flags and 3 flags are control flags. The conditional flags are zero flag, sign flag, auxiliary carry flag, parity flag, overflow flag. Okay, so these are all the conditional flags. Okay. So, and the control flags are T flag, trap flag, direction flag, and interrupt flag. These are the control flags. See, trap flag, it is used for single stepping to the program, and this is used basically for debugging the program. And direction flag, using the direction flag, you can process the array in the low address or from the higher address to the lower address. So you can change the processing of the array either from the lower element to the higher element or from higher element to the lower element. And interrupt flag, you can disable or enable the interrupt facility in the microprocessor. So the various features of this flag register we will discuss in the next lecture. Okay. So we have discussed about the general architecture of 8086. We have discussed about the registers. We have discussed about the flag register, and in next class we will discuss about the flag register aspects in more detail. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.